Okay, for this PowerPoint slash video, we're going to talk about something pretty important and something pretty cool. Um, Something that hopefully you haven't been exposed to already, and that is something called the interquartile range. However, before we really kind of get started about talking about what that interquartile range is, I want us to start with a couple questions. Here are the questions that I wanted us to think about. The first question is this. So we recently talked about these two measurements of variation. We talked about the range. We talked about the standard deviation. Before that, we talked about this mean and the median. What was the distinction between the mean and the median? Remember, the median was this resistant measurement. The mean was not resistant. The fact that the mean was not resistant meant that it was unduly influenced, and we saw this in an example. It's unduly influenced by just even a handful of extremely large or extremely small observations. We saw the median was resistant. It was not unduly influenced by these. And so we also made this observation that the mean has this magical property. We'll talk about the magical property down the road. And that magical property makes it so that we want to use the mean whenever we can. It's just we can't for skewed distributions. And so we ultimately concluded that, right, we use the median for skewed distributions. We use the mean for distributions that aren't skewed, or, right, for these symmetric distributions. Now I want to talk about this idea for measurements of spread. First off, do you think the range is appropriate for skewed data? To phrase it another way, do you think that the range is resistant? Yeah, exactly. There's no way, right, that it's resistant. It's about as unresistant as something could possibly be. Remember, the range is defined as the largest value minus the smallest value. That is, only two numbers go into the actual calculation of the range, and those are the biggest number and the smallest number. So of course it's going to be inordinately influenced by, right, the biggest number and the smallest number in the data set. What about the standard deviation? Do you think that that's appropriate for a skewed data? Do you think the standard deviation is resistant? Well, here it's maybe a little more subtle than the other one, but the answer is going to be no. And one way to think about it is what? The standard deviation is a house built upon the foundation of the sample mean, right? Remember that the interpretation of the standard deviation is the average distance of the observations from the sample mean, right? So its whole definition, its whole identity is built around the sample mean. We know that the sample mean is inappropriate for skewed data, and hence it should be maybe a little bit intuitive that anything based off the sample mean should also be inappropriate for skewed data. Ah, dear. Well, then what's a researcher to do, especially if they do come across skewed data? We know if we want to measure center that we should use the median, but what would we do if we also wanted to in some way measure spread? Dun da da da, and here it is, rushing to our rescue, the interquartile range. Not only a resistant measurement of spread, that is not only a measurement of spread that we can use should we hearken across, should we stub our toe on a data distribution that has a skewed shape to it, but also something that appears to have calmed the fussy baby that you may or may not have heard in the previous two slides. So the interquartile range, not only our resistant measurement of spread, but also perhaps the passy or swaddle of descriptive statistics.
So, before we talk about the interquartile range, we need to talk about something called quartiles. There are two quartiles. There's the first quartile and the third quartile. These are also, depending on the textbook, sometimes referred to as the lower quartile, that would be the first quartile, or they're referred to as the upper quartile, that would be the third quartile. So the first or lower quartile is defined to be the 25th percentile. The 25th percentile means that 25% of the data set, 25% of the numbers, 25% of the sample is below that quartile. Alternatively, 75% of the data set or the numbers are above it. The third quartile, aka the upper quartile, is defined as the 75th percentile. That is, 75% of the data is below it, 25% of the data is above it. So how do we calculate quartiles? Well, I actually think this is one of the cooler things we do in the class, because I feel this is a kind of a classic use of the broader concept or the big picture idea of mathematical reasoning. How do we do something like calculate quartiles, something that's foreign to us and we've never seen before? Well, if we could take the problem of finding quartiles and reconceptualize it, rephrase it into a problem that involves finding medians, then we're golden, because we've already perfected the skill of finding medians. And it turns out that we can do exactly that. So finding quartiles, we're going to see, is no different than finding medians. The first thing we do is we find the median of the dataset. Remember, the median of the dataset is that middlemost number. It's the 50th percentile. It breaks our dataset in half. We now have a lower dataset, and we now have an upper dataset. Right, the lower dataset is the lower 50% of our data. The upper dataset is the upper 50%. If we now find the median of the lower dataset, it turns out that that will be the lower quartile. Does that make sense? Well, remember, that lower dataset is ranging from sort of the 0th percentile to the 50th percentile. And what's between 0 and 50? 25%, right? So the median of that lower dataset is the 25th percentile. For our upper dataset, that ranges from the 50th percentile to the 100th percentile. What's between 50 and 100? Well, it's 75. So the middle, right? The middle of that upper dataset, the median of that upper dataset is the 75th percentile. That is, finding quartiles is no different than the sort of sequential process of finding medians. So let's do some examples. So let's say that we take a survey of 10 nurses, and we ask them how many months have they been at their current job. And we have the following results, right? The first nurse says that he or she has been there 23 months. Second nurse hasn't been there nearly as long. They've only been there 2 months. Third nurse has been there 5 months, and so on. So, next slide, we'll see how to find the lower and upper quartile of this data set or this variable. So here it is. Remember, we want to find a median. Before we can find a median, we have to order the numbers. If you look back at the previous slide, the numbers were not ordered. Here, I took the liberties of ordering them. So I took all those numbers and I ordered them from smallest to largest. This allows me to find the median. Now, we have 10 nurses. That's an even number, which means that there's going to be 2 numbers in the middle. In this case, I bold-faced them. It's 14 and 23. So the median is the number that falls exactly between 14 and 23. I can find that by adding up 14 and 23 dividing by 2. If I do that, I get 18.5. 18.5 is the number exactly between 14 and 23. Now, 18.5 is exactly between 14 and 23. So I want to sort of think of this. I want to visualize this as almost like a kung fu mathematics move. Aya! We strike the data set with ninja-like precision right between the 14 and the 23, essentially breaking the data set into 2 pieces. I color-coded it. The red numbers are the lower 50 percentile. So that's the 2, 5, 8, 12, and 14. The upper data set is the green numbers. That's the 23, 25, 27, 36, and 42. Remember, the first quartile is the median of the lower data set. So the first quartile, I'm abbreviating it Q1, is going to be 8. The third quartile, I'm abbreviating it Q3, is going to be 27. Let's try a second hospital. So same survey at a different hospital. Call this hospital B on 7 nurses. We get the following results. Here I made our life a little bit easier. I ordered it to begin with. So on the next slide, let's really do the exact same process. So the numbers were already ordered. Once I have them ordered, I can find the median. Here there's 7 nurses. 7 is an odd number, so there will be a single middlemost number. In this case, it's 23. So the median is 23. Now in this case, the median is the actual number 23. So when I do my ninja strike, yeah, brace yourself, it's going to be right on the number 23. Ah! Right there. The key-up's very important. On the 23. Now, obviously a blow of that magnitude and that power, there's no way the number 23 is going to survive it. So that number 23 is essentially destroyed. It's not going to be in my lower data set. It's not going to be in my upper data set. And you can see that with how I color-coded it. The lower data set is just the 7, 11, and 20. The upper data set is just the 26, 28, 29. The first quartile is the median of the lower data set. That's 11. The third quartile is the median of the upper, the green data set. That's 28. I know, pretty easy, right? Done and done. Now, what do we do with the quartiles? Well, we could take the quartiles and we could create something called the interquartile range. The interquartile range is the spread, the distance, the range of the middle 50% of the data. It's mathematically defined as that upper quartile minus the lower quartile. Right? That is, the interquartile range, often abbreviated IQR, interquartile range, is Q3 minus Q1. Now, the interquartile range is useful as a description or measurement of variation in cases where the median is appropriate. When is the median appropriate? Exactly when we have a skewed distribution. Right? The interquartile range conceptually is similar to the range. But remember, the range was problematic because it used the biggest number and the smallest number, which meant that it was susceptible to a really big or a really small number. The interquartile range sort of ignores the largest numbers. It sort of ignores the smallest numbers and instead focuses on sort of that middle 50%, sort of the, quote, average values. By doing so, by ignoring the really big numbers, by ignoring the really small numbers, we're essentially creating an intuitive measurement of variation that is essentially resistant. So how do we compute the interquartile range for the previous 2 examples? Well, Hospital A, the interquartile range, again, this is going back to the previous slides. The third quartile for Hospital A was 27. The third quartile was 27. The first quartile was 8, so the interquartile range is 27 minus 8, or 19. For Hospital B, the third quartile was 28. The first quartile was 11, so the interquartile range is 28 minus 11. That's 17. We can also use these quartiles to create something called the 5-number summary. The 5-number summary are these 5 numbers. I do like to ask a question on the test, asking what the 5-number summary is. If you remember what the 5 numbers are, they're very, very easy to compute. If you don't remember, you're going to unfortunately be in trouble. So try to remember this going into your test. The 5-number summary are 1, the minimum value, 2, the lower quartile, 3, the median, 4, the upper quartile, 5, the maximum value. So the 5-number summary essentially breaks your data set into quarters. It quarters your data set. That's where the word quartile comes from. These 5 numbers are a nice way of describing a particular data set, and in particular, they could be visually combined to create something called a box plot, also sometimes called a box and whisker plot. So let's take a look at a few slides to see what that is. But before we do it, let's do the 5-number summary for the previous 2 examples. So again, to get some of these numbers, you would have to look back at the previous PowerPoint. But if you look at it, you'll see the smallest number is 2. We had found the first and third quartile as well as the median, and I just reproduced those numbers. And if you look back at the original slide, you'll see the maximum value is 42. Hospital B, I'll leave it to you to confirm this. We just did the first and third quartile as well as the median. If you look at the slide for the nurses from Hospital B, you'll see the minimum and maximum are 7 and 29.
So we can use the information from that 5-number summary to create something called a box plot, which we'll talk about how to do in the next few slides. Box plots are useful ways of visually or graphically showing average and spread of a distribution, but they're probably most commonly used, they're probably at their most powerful, when they're used for side-by-side comparisons of different distributions, or side-by-side comparisons of different groups. We'll see in this example we're gonna do a side-by-side comparison of Hospital A versus Hospital B. So when we're gonna focus on for this PowerPoint. But if you look at your textbook, there should also be another 1 or 2 examples of these sort of side-by-side comparisons. So that's sort of really kind of the main utility of these box plots that we're getting ready to learn how to make.
So actually, I guess next slide is where we'll see the box plots. And so here they are. So we have Hospital A, it's on the left. We have Hospital B, which is on the right. We have the actual numbers. This corresponds to the months that the nurses have worked there along the left. So let's focus on Hospital A. The way the box plot works is you have that middle box, agreed? If you look at the lower line of that middle box, it's right around the number 8. That's the first quartile. If you look at the upper line of the box, you'll see that looks like it's roughly around 27. That's the third quartile. The darker, bold-faced line in the middle of the box, that's the median, which is at 18.5. So the boxes are moving up: first quartile, median, third quartile. Now coming out of the box, you see a couple lines. They look a little bit like whiskers, don't they? Meow, which is why it's called a box and whisker plot. The whiskers go out to the minimum value, and the maximum value. So the minimum value in this case is 2, so that lower whisker goes down to 2. The maximum value for Hospital A was 42, so that upper whisker goes all the way up to 42. Right? So in the box and whisker plot, I can see all 5 numbers from my 5-number summary. I can see the minimum, the maximum, the first quartile, the third quartile, and I can also see the median. I can also see a number of other things, right? The actual width of the box, the distance from the first quartile to the third quartile, that's the interquartile range. The length from whisker to whisker is the actual range, right? That's the minimum, or the maximum, sorry, minus the minimum. So I can see not only the 5 numbers, but I can also see quickly and easily the interquartile range as well as the actual range. It's the exact same analogy with Hospital B. I'll leave it to you to verify, right, where all those lines should be, where the whiskers should be leading to. Now, my claim was that box plots are useful for side-by-side comparisons, and they are. I can look at this box plot and I could say, which hospital seems to be more popular with its employees, right? Which is essentially asking, which hospital, on average, do the nurses work at the longest? Right? Using that idea of if they work there longer, then that's maybe indicative of a higher level of job satisfaction. That's really just comparing averages, right? In this case, that's just comparing medians. So I can see quite clearly that the median for Hospital B is larger than the median for Hospital A. Which means that, right, I might conclude that workers at Hospital B seem to be happier. I might say, which hospital has the most variation? I could answer that question in a couple ways. I could compare ranges. Remember, the range is the distance from whisker to whisker. If I do that, Hospital A, I can see quite clearly, has a much larger range than Hospital B. But remember, range can be very deceptive. Range is not a resistant measurement of variation. I would discourage you from using it. Really, the fact that Hospital A has such a long whisker is really just that one person that's been there, right, for 42 months. If I focus on the interquartile range, if I focus on that middle 50%, that's really just comparing the length of the boxes, right? And I can conclude that the boxes, right, the boxes have roughly the same length. It is true that hospital A has a slightly larger interquartile range. I think it was 19 versus 17 for hospital B. So technically A is a little larger, but we might say that their lengths are very comparable, which might mean that the overall variation is somewhat similar, with hospital A having perhaps slightly more variation when comparing interquartile ranges.
All right, so after all that rigmarole, we're finally here. We're really finally at the punchline, and the punchline's going to really tie together a lot of what we've been talking about, right? So we've hopefully motivated the following fact. We've hopefully motivated the following fact that if we want to describe a particular variable, there's really at least two characteristics that we need to be focused on, right? We need to focus on this idea of average. We need to focus on this idea of spread. Now, how we approach this problem, right, how we measure these concepts, it depends. It depends upon whether we're working with a symmetric variable or a skewed variable. Now, how do we discern which of these two cases it is? Well, again, that goes back to the histogram, doesn't it? We saw that it's really the shape of the histogram that helps us determine symmetric or skewed. That is, this slide beautifully ties together, right? It ties together histograms, it ties together measurements of average, it ties together measurements of spread. It brings it all together. Now, if we're working with a symmetric data set, then jackpot, we're good. In fact, we're better than good. We're golden. In this case, we could use sort of our best measurement of average. That's the mean. And we pair with that mean the standard deviation, right? Those are the two measurements that go together. Now, if it's a skewed distribution, well, as we've seen, the mean is inappropriate. The mean will give a distorted picture of average. So we're forced to use the next best measurement of average. We're forced to use that median. And what we do in addition to that is we pair it up with the interquartile range. The interquartile range, it pairs with the median as beautifully as a Pinot Grigio pairs with a seafood tostada. And these two numbers come together, and for a situation where the data set's skewed, they appropriately paint a picture of center and spread. Alternatively, we might present the 5-number summary or a box plot, and we know sort of contained within that 5-number summary or contained within that box plot is the median, the interquartile range, as well as maybe a little bit of extra information. So that's a lot, right? That's a lot for us to think about. I would encourage you to go maybe take a nap, give that tired brain of yours a rest, or maybe I don't know, maybe go eat some cake. Go celebrate and rest, and at some point return as we continue ever onward with our beautiful discussions of our beloved statistics.